All right, so the percent yield is the actual yield over the theoretical yield times 100%. And so in the cookies, what was our percent yield for the cookies? Was it 99% yield? What was the percent yield? Talking about the last class. Yeah. Yeah, for 100 cookies. If we bake 100 cookies, how many do we actually get? No, not that one, the one before that. 90 out of 100, so we lose 10. So we have 90%. That's the same thing as this. So let's say you're baking cookies and you only have a 61% yield. So that means out of 100 cookies that you make, you're only going to get 61 of those. What happened to the other 39? Well, probably people ate them, or you left some batter in the bowl, or some got broken. You know, you got some loss. You lost 39 out of 100. Right? And so that's a 61% yield. So only 61 cookies out of 100. So in terms of product, what is the product we're interested in here? Chlorine. We're interested in the chlorine. So if it's a 61% yield of product, then we're going to change this. We're going to change this from 61 grams of product. We're going to say 61 grams of chlorine. So 61 grams of chlorine. Well, chlorine is going to be this product over here. It's Cl2. 61 grams of chlorine for every 100 grams of what? No, not an HCl. It's like the cookies. It's exactly like the cookies. If you had a 61% yield of cookies, that means you got 61 cookies out of 100 what? You got 61 cookies out of 100 cookies. And so it's the same thing. We get 61 grams of chlorine out of 100 grams of chlorine, but we have to put labels on this. Otherwise, it makes no sense. What are the labels we're going to put on this? And so the other one, if you look back to what we did earlier, it was 90 cookies for every 100 cookies. Well, that makes no sense. And so we put labels on it. What were the labels we put on them? Yes, we're going to get 90 cookies actual for every 100 in theory that we make. And so it's the exact same thing here. For every 61 grams of chlorine we actually get, we better be prepared to make 100 because we're going to lose some. And so let's say I had a 61% yield of cookies. If I want 61 cookies, then I better plan on baking 100 cookies because I'm going to lose some. What if I want 100 cookies? Well, then I'm going to have to make well over 100. And so this is the 61%. It's 61 grams of chlorine actual yield for every 100 grams of chlorine theoretical yield. Well, let's ignore this for right now, this 9.6%, and then go down here. This is 105 kilograms of chlorine. Is that what we want to actually get, or is that what theoretically we should get? Is this going to be actual yield or theoretical yield at the bottom? This is, yeah, we want to obtain 105. If we want to obtain 105, then we got to make more. We got to make more. And so if we want to obtain 105 kilograms, so we call that 105 kilograms chlorine actual yield, AY. 105 kilograms of chlorine actual yield. Well, let's convert from kilograms to grams. So this will be 1,000 grams per kilogram. And this is not dependent on chlorine, so I'm not going to write chlorine there. And that's going to give me grams of chlorine actual yield. And then here's where I'm going to put this in. that means for every 61 grams of chlorine actual yield, I better make 100 grams of chlorine theoretical yield. And so let's say I wanted 100 cookies and I had this yield. If I want 100 cookies actual yield, then I have to realize that for every 61 cookies actual yield, I better bake 100 cookies theoretical. So this is theoretical, this is actual. And so this is how much batter I'm going to have to prepare, because I'm going to have some losses. And so if I want 100 cookies actual yield, then in theory, I better try to make, let's see what that comes out to. 100 times 100 divided by 61. I better be prepared to make 164 cookies, 163.9. And so I better make 164 cookies because I'm going to lose 64 of the cookies. And I'm only going to end up with 100 cookies. That's because it's kind of a 4% yield. If you're a bakery and you have this kind of loss, it's kind of a big loss. But in chemistry, we're going to have big losses sometimes. It's hard to control industrial processes. And so this means that if I want 105 kilograms, let's see, 105, the ratio is this, so I'm just going to do times 100 divided by 61. If I want 105 kilograms, I better be prepared to make 172 kilograms. Does that make sense? Or not really?
I thought we changed it to grams.
We did. And so 172,000 grams, which is 172 kilograms. But I changed it to grams because I like the grams. All right, then what we want to know is sodium chloride. How much sodium chloride do we need? And so we're going to go from grams of chlorine, theoretical yield is what we do in stoichiometry. And so we're going to go from grams of chlorine to moles of chlorine. And so chlorine's molar mass is 1 mole of chlorine, pure chlorine, is 35.45 times 2 is 70.90 grams. And so we go to moles of chlorine. And then from moles of chlorine, we'll go to moles of sodium chloride. And there's 2 moles of sodium chloride for every 1 mole of chlorine. And then we'll go to grams of sodium chloride. Well, sodium is 22.99. Chlorine is 35.45. So what does this give us? 50, 57, 58. 58.44. And so it's 58.44 grams of pure sodium chloride per mole of pure sodium chloride. But do we have pure sodium chloride? What massive solution then is 9.6% sodium chloride? It's not pure sodium chloride, it's a mixture. In this mixture, they tell us the composition. And so now you can tell me, what is the second percentage here? How would I write that? It's going to be 9.6 grams out of 100 grams of what? 9.6 grams of what out of 100 grams of what? Yeah, 9.6 grams of pure NaCl per 100 grams of NaCl mixture or NaCl solution. That's what we have. NaCl solution. Solutions are mixtures. And so we can add this here. We can get for every 100 grams of NaCl solution, we only have 9.6 grams of pure NaCl contained in that solution. And so these are the 2 percentages we're going to use. This one comes from the 61% yield. This one comes from 9.6% sodium chloride. So those are so this is what we call an advanced problem. It's an advanced problem because it's so easy to get these percentages mixed up. And it's so easy to get them mixed up, and people mix them up all the time and end up getting screwed up. And so your book likes to leave things in kilograms, kilomoles, and that kind of stuff. But looking at the book's answer, this is, you see they write actual. I wrote AY for actual yield. They write ACT for actual. So this is what we want to actually get. If we want to actually get that, then we have to take into account the percent yield. So for every 61 kilograms actual, we have to have 100 kilograms theoretical. And then the theoretical is what we have in stoichiometry. And then this gives us the pure sodium chloride here, but we're not dealing with pure sodium chloride, we're dealing with the solution. It's going to be 9.6 grams or 9.6 kilograms for every 100 kilograms or grams of solution. I like to keep things in grams, so that's why I don't like to do it that way. There's something nice about repetition, saying, the same kind of thing over and over again. So this is why I like to do it. And add a couple of steps, but you see the same familiar center or heart of stoichiometry, mole conversion. I don't like kilomole to kilomole conversions. Well, let's see some of the other percentage problems to see if there are any other variations of this that we'll encounter. We don't have much time. A dry mixture of hydrogen chloride and air is passed over a heated catalyst in the Deacon process for manufacturing chlorine. Oxidation occurs by the following reaction if the conversion is 63% complete. So what is that? 63% complete means 63% yield. That's what that means. How many tons of chlorine can be recovered from 1.4 tons of HCl? And so this one is easier than the previous one. This one is for every 63 grams of chlorine, we better produce 100 grams of chlorine. So for every 63 grams of actual yield, AY, for chlorine, we better produce 100 grams of theoretical yield of chlorine.
Chlorine CO2.
Yeah, in this case, chlorine CO2. We want the chlorine product, which is at the end here. 83. Fluorides retard tooth decay by forming hard acid-resistant calcium fluoride. Calcium fluoride is pretty insoluble and unreactive. Layer in the reaction. So we take our stannous fluoride or tin 2 fluoride and calcium hydroxide, which is in teeth, to make calcium fluoride, stannous hydroxide. If at the time of treatment there are 239 milligrams of calcium hydroxide on the teeth, and the dentist uses a mixture that contains 305 milligrams of tin 2 fluoride, has enough of the mixture been used to convert all the calcium hydroxide? If no, okay. This is just a limiting reagent problem. Which one's the limiting reagent? Obviously, we want the calcium hydroxide to be the limiting reagent because we want to protect all of the teeth. We convert all the calcium hydroxide in the teeth. And so this one, we just got to figure out the yield from calcium hydroxide and the yield from stannous fluoride and which one's the smaller amount. And so if it turns out that the stannous fluoride is the limiting reagent, we didn't have enough. So we got to add more. So this is a limiting reagent problem. There's no percentages in this one. We're out of time, so 84, 85. Let's take a look at some of the more challenging problems. Yeah.